Okay, am I recording this? I'm recording it. Okay, so let's share computer sound so you can hear it.
This is the most complex and sophisticated machine ever made. In 6 minutes, it will be traveling at 17,500 miles an hour. In 8 minutes, the humans inside will no longer feel the pull of the Earth's gravity.
Okay, so space shuttle launch takes about 8 minutes. All right, so what happens within that 8 minutes? Within that 8 minutes, you travel 180 miles while reaching the final speed of 17,500 miles per hour. So these are the limits within which the space shuttle has to fly.
It is such a tremendous amount of energy, yet the limits within which it must fly are very, very narrow. So you've got something that's powerful, but delicate at the same time.
The propellants that they use on the space shuttle are very, very potent, and it's like a gigantic controlled explosion that lasts for 8 minutes to get you into orbit. The space shuttle main engines are a very incredible device. They generate enough force to levitate 200 cars, and they could hover them stationary in midair. The fuel amount used is tremendous. The turbo pumps that supply fuel to the engines pump enough liquid it could drain a swimming pool in less than 30 seconds.
Space begins at the edge of the Earth's atmosphere, 50 miles straight up. But the shuttle orbits at an altitude of about 180 miles.
We've become accustomed to seeing the shuttle up there, seemingly suspended, hardly moving. Yet the astronauts are traveling around the Earth at 18,000 miles an hour. And as they go about their work, they can glance up at 16 sunrises in a single day.
You're muted.
You're muted.
Okay, guys, give yourselves 2 points for letting me know. All right, so we got 8 minutes to travel 180 miles, right? While reaching the final speed of 17,500 miles per hour. Okay, so that's what we got. So we got 8 minutes to travel 180 miles while reaching the final speed of 17,500 miles per hour. Okay, that's where we're at. All right, so these are the limits within which the space shuttle has to fly. And one of the things that you need to realize is within this 8 minutes, no one is piloting the space shuttle. No one is piloting the space shuttle under the circumstances. All right, so now for you to be able to carry out something this complicated without anyone piloting the space shuttle, what you need to do is you need to make every single aspect of motion predictable within that 8 minutes. So how does NASA make motion predictable? How does anyone make motion predictable? How does that go? How does that work? All right, so
2, 1, and liftoff. Liftoff of the 25th space shuttle mission. And it is
But what started out as a grand achievement for NASA, 73 seconds later turned into a national tragedy.
all right, notice that in this case, they were able to get 73 seconds of predictable motion. I mean, when you're dealing with rockets, and just because you got rockets doesn't mean that you're going anywhere.
Rockets aren't new. Neither is the idea of riding them to the heavens. One night in the 16th century, a Chinese nobleman, Wan Hu, prepared himself for liftoff. But then there was, as modern spacemen say, a glitch. And though Wan Hu didn't make it to the stars, he couldn't be found on the face of the Earth either.
All right, so basically what happened was they had the right idea. So you need to have rockets. But in essence, if you're dealing with rockets, you're dealing with explosives. So what you need to do is you need to take something chaotic, like explosives, and then you need to make predictable motion out of it. So how's that possible? How do you go from something which is relatively unpredictable into something that becomes predictable?
However, as the satellite's now expected to smash into Quasi, an uninhabited part of the Australian outback. Scientists say.
All right, predictable motion allows forecasting. In the sense that not only are you going to know where in this case, the satellite is going to land, you'll know exactly when it's going to land, how fast it's going to land. Okay, this is 100% predictable. This guy is on the landing spot, so he's ready for impact. Notice he's got pillows and everything else.
Yahoo?
Notice that not only is he ready for impact, also his dog is ready for impact. Now, this is predictable motion. So how do you go from something unpredictable to predictable motion? How do you make motion predictable? All right, so it's an extension of the lecture that we have. All right, so change in displacement in time is your velocity. So measure distance over measure time is going to be your velocity. And if your velocity is changing in time, that's going to give you your average acceleration. So the question, so speeding up is going to be acceleration. Change in direction is going to be acceleration. And in this case, not only your direction is changing in time, also your velocity is changing in time. So that's also acceleration. And notice at this point, your velocity is about to change in time. All right, so change in velocity in time, what is that called? Oh, okay, so change in velocity in time is a technical term, which is known as jerk. The motion itself is known as jerking motion. So change in acceleration in time is known as jerk. The motion itself is called jerking motion. All right, I just noticed that I'm supposed to be connected to, iPad was supposed to be connected. All right, guys, just give me a minute. All right, let me just get out of here. The measured values are on the right. On the left, you will have the average values. Okay, so the thing about jerking motion is it's unpredictable motion. It's chaotic. Everything is going to be all over the place. Example of jerking motion is car collisions. Within 1/10 of a second, what happens? The car is going to crumple. Different portions of the engine compartment is going to crumple at different rates. So which means that within 1/10 of a second, you're going to end up experiencing jerk. Which means that you're going to end up experiencing all these vibrations all over the place. All right, so this is your time axis. I'm going to express it in terms of seconds. And this is going to be our acceleration axis. And we'll express this in terms of g. All right, so the acceleration is going to keep varying within that time period. All right, so here's what I'm looking at. So the impact starts, the car is going to start to crumple, and then boom, it's going to crunch, crumple, crunch. And then notice that the acceleration is going to keep varying up and down, and then the motion is going to start to die off at some point. Okay, the entire thing that you're looking at is going to last only 1/10 of a second. All right, so that's the car collision impact. Crumple zone is going to crunch. Now the maximum value of the acceleration is going to be here somewhere. All right, so here's the maximum value that you're looking at. And it's going to be maybe about 150 Gs that you're looking at, all right, in the negative. So it's going to be 150 Gs. And this is happening at 40 to 50 miles per hour. So the acceleration value is going to be 150 Gs. So the question for you guys is this survivable? Is this something survivable? What do you think?
Yes,
Yeah, I think so.
Why?
because
Well, impact time is very, very diminutive. It's very small.
It's 150 Gs though, right? So can you survive 150 Gs? Yes or no?
If you're wearing a seatbelt, you might.
All right, guys, this is the car's acceleration. Can you survive 150 Gs?
No.
Answer to that question is no. Okay, this is one of the mistakes that Mythbusters kept making, the original Mythbusters, for years. It used to drive me nuts. They would have these accelerometers, and then they would just activate when you hit 100 Gs, and they would say, hey, this is dead upon impact. No, guys, this is your instantaneous acceleration. All right, this is 150 Gs. This is the maximum value that you can attain. What we are interested in is not your maximum acceleration. We're interested in the average acceleration. So your average acceleration, because the acceleration, notice that the acceleration keeps varying. It keeps going up and down, up and down, up and down, up and down. So there's always a change in acceleration. So what we're interested in is your average acceleration. What is the average acceleration during this time period? This so happens the average acceleration within this time period is going to be somewhere here. So you're looking at maybe about 20 Gs, 25 Gs. All right, so we're not interested in the maximum acceleration. We are interested in your average acceleration within this range. And the average acceleration, I mean, the larger the time period is, all right, the smaller the average acceleration is going to become. So what happens when there's jerk in motion? Okay, this simply means that the acceleration is changing in time. When the acceleration keeps changing in time, notice that it goes down, goes up, goes down, goes up, goes down, goes up, and the values keep changing. When there's something like that, the only thing you have to do is you have to get an estimate of what the average acceleration is. So if there's jerk in motion, what you need to do is just use that. Got it? So if there's jerk, then what do? You have to use the average acceleration formula to get an estimate. Okay, so jerking motion formula is more of a mathematical model. All right, so if there's change in acceleration, A, use the average acceleration formula. That's what it means, and that's exactly what we did. All right, so when you're using the average acceleration formula, there's an implication. The implication is that there's change in acceleration. All right, so what do we know? Change in acceleration in time is called jerk. All right, so if there's jerking motion, what do? We use the average acceleration. So the example of jerking motion is car collisions. Got it? So when the car is crumpling, there's a change in acceleration. All right, pick the best answer, put your responses in the chat. Ooh, pick the best answer and put your responses in the chat. Okay, very good. I see a lot of C's. Going down, going down. All right, C, all the way through. C is the best answer. All right, give yourself 5 points for that one. All right, in the jerking motion formula, initial and the final accelerations are usually the measured accelerations. Remember, guys, always on the right-hand side, you have the measured values. Measured values are always instantaneous values. Got it? So what do we have on the right-hand side? We have the instantaneous accelerations on the right-hand side. So the best answer is C. Those of you guys who pick C, give yourselves 5 points for that one. All right, so C is the best answer for that one. All right, you guys got this one right. In reality, if the acceleration keeps changing during motion, then the only thing that makes sense to use is the average acceleration, right? So average acceleration formula is used, so give yourselves 5 points for that one. That's actually really, really good. All right, perfect. All right, this is a good time to take a break. So go take a break for 10 minutes. All right, if the acceleration is changing in time, what do we call that?
Jerking.
It's called jerk motion. It's called jerking motion. All right. So the next step is, how does one make motion predictable? Okay, you make motion predictable by getting rid of jerk stuff. So how do you get rid of jerk? You get rid of jerk, in essence, by making the acceleration constant. All right, so if you make the acceleration constant, motion itself becomes predictable.
I'm sorry, can you repeat that? How do you make motion predictable again? I'm sorry.
All right, so how do we make motion predictable? You make motion predictable by getting rid of jerk, right? All right, so jerk is what makes motion unpredictable. Notice that you end up, acceleration keeps changing in time. So you don't
motion becomes predictable when acceleration is made constant.
Very good. The motion is made predictable if there's no change in acceleration. So if there's no change in acceleration, jerk becomes 0, right? So how do you make motion predictable? You make motion predictable by
making acceleration constant.
Right. So you make motion predictable by eliminating jerk. All right, so if you make jerk 0, then the motion becomes predictable. All right, so the next question is, how do you make jerk 0? All right, so you eliminate jerk, and if you eliminate jerk, the motion itself becomes predictable. The only way you can eliminate jerk is if you make the change in acceleration 0. All right, so the only way you're going to be able to do that is making sure that this section, the change in acceleration is 0. All right, so the motion is going to become predictable when the acceleration is fixed.